Okay, this is project test 6, video number 3, problems 21 to 30. Researchers working for certain airlines investigate the weight of carry-on bags. The researchers will use the mean weight of a random sample of 800 carry-on bags to estimate the mean weight of all carry-on bags for the airline. Which of the following best describes the effect on bias and the variance of the estimator if the researchers increase the sample size to 300? First off, let's address bias. Bias is not affected by sample size. Sample size does not impact bias. So bias will increase or decrease, can't be those. Bias will decrease, so now we're down to C and D because it's remained the same. Now, standard deviation. Remember, it's essentially S divided by the square root of N. So as N increases, our standard error decreases, or the variation decreases. Or perhaps a better way to look at it is if we were doing a confidence interval, X bar plus or minus T star, S divided by the square root of N. As N increases, our margin of error decreases. So as N goes up, ME goes down. Why? My standard error goes down. So if I have a sample size 1300, the variation will decrease. The variation will decrease. Sampling error diminishes. As N goes up, sampling error goes down. And that's the same as saying sample variation. Please remember, sample size has no impact on bias. Number 22, researchers investigated whether a new process for producing yarn could reduce the mean amount of volatile organic compounds emitted by carpet. From random samples of carpets, the researchers found the mean reduction of VOCs emitted by carpets made with yarn produced by the new process compared with that of carpets made with yarn produced by the traditional process was 13 parts per million. All conditions for inference were met, and the p-value for the appropriate hypothesis test was 0.095. Which of the following is the best interpretation of the p-value? Remember, p-value is the probability we get a test statistic this extreme or more extreme in favor of the alternative. So at least as extreme as in favor of the alternative. All right. The probability of null hypothesis is true. No. The probability of the alternative, no. It's the probability of getting a test statistic this extreme or more extreme, or at least this extreme, if the null is true. All right. It's not the probability of observing a mean reduction. It's the probability of observing a mean reduction if the null is true. If the null is true. If the null hypothesis is true, hey, the probability of observing a mean reduction of at least 13 parts. I'm liking this one a lot. If the null hypothesis is true, the probability of observing at most. No, it's at least, or at as great or greater. All right, not less than. So this is number 22 is D. Number 23, a 99% one sample Z interval for proportion will be created from the point estimate obtained from each of two random samples selected from the same population. Sample R and sample S. Let R represent a random sample of size 1000 and let S represent a random sample of size 4000. If the point estimate obtained from R is equal to the point estimate obtained from S, which of the following must be true? So basically, here's what they're saying. We're collecting a random sample, And we have p hat plus or minus z star p hat q hat over n. Well, they're telling us the point estimate for R and S are the same. So this is equal, and this is equal. The only thing that's changing is our sample size. So we are going from a sample size, R has a sample size of 1,000, S has a sample size of 4,000. This one, because as n goes down, our interval is wider. Or as n goes up, I should say interval. As n goes up, our interval is narrower. So we know that this one is going to be wider. R will be wider than S. This has less variation. This has more variation. The question is, how much? Well, the easiest way is to set this up as a ratio, and it depends on how you set it up as to which answer you're going to get. But you have to know which is which. So I'm going to label this R, and I'm going to label this S. And I go, well, those all cross out. And using some fancy math, I end up with the square root of 1 over the square root of 4. So 1/2. So S will be half as wide as R. S will be half as wide as R. Remember, it's wider the smaller the sample size. The smaller the sample size is wider. So S is half the width of R, or R is 2 times the width of S. Those mean exactly the same thing. So the margin of S will be 4 times, no. The margin of S will be 2 times, no. The margin of S will be equal, no. The margin of error for R will be 4 times, no. The margin of error will be 2 times. So set a ratio, but make sure you know which one's wider. The one with the smaller sample size is wider, so R had to be wider. And so S is half as wide as R. R is twice as wide as S. Okay. Number 24. A study was conducted to evaluate the impact of taking nutritional supplements on a person's reaction time. 100 volunteers were placed into one of 3 groups according to their athletic ability. So we're placing them into groups: low, moderate, and high. Low, moderate, and high. Participants in each group were randomly assigned. Ooh, I like that phrase, randomly assigned. If I'm randomly assigning something, because I use the word random assignment, this is an experiment. Okay, now I grouped. And if you're grouping, and you're grouping it based on low, moderate, or high, it can only either be a stratified or a block. But we use block for experiments and stratified for observational studies. We already said this was an experiment. So because we grouped and we had random assignment tells me it's an experiment. We grouped it. So either it's going to be stratified or block. And it's like, you know what? Experiments is the one that has blocks. It has to be block, because block goes with experiments. Stratified only goes with observational studies. Stratified does not go with experiments. Since this is an experiment, we have a randomized block design. All right, number 25. The number of tickets purchased by a customer for a musical performance at a certain concert hall can be considered a random variable. The table below shows the relative frequency distribution for the number of tickets purchased by a customer. So a single customer, there's a 20% chance they'll purchase one, 45% chance they'll purchase two, all the way up to a 5% chance that they'll purchase five. Suppose each ticket for a certain musical costs $12. Based on the distribution, what's the cost, mean cost per customer for the performance? So here's what I did. I went ahead and put them in a stat edit, 1, 2, 3, 4, and then I'll put the probabilities here. Because what I'm going to do is I'm going to go 1 times 0.2 plus 2 times 0.45 plus 3 times 0.10 plus 4 times 0.20 plus 5 times 0.05. And this is going to give me my expected value. And this will tell me how many tickets I expect them to buy. And I did that in a calculator. I put 1, 2, 3, 4, 5, 0.2, 0.45, etc. So I just entered the table in there. Stat calc, one variable statistics. I have a list of L1. And now I have a frequency in L2, so second 2. And I get an X bar of 2.45. So on average, I expect them to purchase 2.45 tickets. But they didn't ask me how many tickets they expected me to buy. They expected what is the cost. So it's going to be 2.45 times the cost. And 2.45 times the 12 gives me $29.40. Oops, circled the wrong thing. $29.40, which is D. So number 25 is D. All right, moving on to 26. A survey of a random sample of 210 male teens and 228 female teens, ages 13 to 17, found that 122 of the male teens and 160 of the female teens brush their teeth at least twice a day. If there is no difference, this is going to key phrase, between the proportion in the population of all male and females ages 13 to 17 who brush their teeth at least twice a day, how many males and females in a sample would be expected to brush their teeth twice a day? So here's what they're saying. HO, proportion of males equals the proportion of females, where PM is the proportion of males who brush their teeth, and PF is the proportion of females. All right, if I'm working with a hypothesis test, I'm going to have to do something a little bit crazy here, and I'll get to that in just a second. But my initial gut reaction, and probably yours too, is to go, you know what? We have 122 over 210. And I'm just going to check, does that equal the 160 over the 228? Because this is the males and this is the females. So I go 122 divided by 210, and I get a value of 0.5809. And over here, I do 160 divided by 228, and I get 0.70. And clearly, those are not equal. But they told me if there is no difference, then what should we do? Well, that's why I wrote down the null hypothesis, because that lets me know, oh, I need to think hypothesis testing. Okay, which means I need to think, well, what is the hypothesis test formula? Well, P hat M minus P hat F over P hat combined, Q hat combined in 1 plus P hat combined, Q hat combined in 2. And what they're asking for is, what is this combined value? Well, the combined value, P hat combined, equals X1 plus X2, or XM for males over X plus X females, over N males plus N females. When I do that, I end up going, okay, we have 122 males out of 210 plus 160 females out of 228, because this provides me my best estimate. So 122 plus 160 equals 282. And by the way, this is one of the more challenging problems that truthfully doesn't bother me a whole lot if you struggle with it. In other words, if you get this wrong at the end of the day, it's not going to matter a whole lot. So 282 divided by 438 equals 0.6438. Well, let's find out the number of females. We had 228. We can't have a part female, so we're going to say about 147 females. And for the males, 0.6438 times the 210 males times 210. And so we would expect there to be about 135 males. So our best answer with this is going to be that I have 147 females and 135 males. And that answer ends up being C, 135 males and 147 females. Once again, how many males is, the trick here is they said, if there is no difference, and it's like, oh, no difference. They're claiming they're equal. Well, I went and checked, and clearly they weren't. So this was a complete waste of my time. They clearly weren't equal. But if I go with the assumption that they're equal, then I have to combine them using this formula to make the combination. And once I have the combination, it's the expected value equals NP. There's my N, there's my P. There's my N, there's my P. And so we ended up with 147 females and 135 males, and answer choice C. All right, number 27. Researchers believe that an increase in lean body mass is associated with an increase in maximal oxygen uptake. A scatter plot of measurements taken from 18 randomly selected college athletes displayed a strong positive linear relationship between the two variables. A significance test for the null hypothesis that the slope of the regression line is 0 versus the alternative that the slope is greater than 0 yielded a p-value of 0.04. That's smaller than 0.05. Which statement is appropriate for the conclusion of the test? The p-value of 0.04 indicates that 4% of the, that's not 4% of the variation. 4% of the variation, if they're talking about variation, we're talking about a different thing, all right? We're talking about the coefficient of determination if we're talking about variation. The p-value of 0.04 indicates that 16% of the variation. Once again, we're talking about the, at that point, we're talking about the R squared. The strong positive linear relationship displayed in the scatter plot, along with a p-value less than 0.05, indicates that college athletes with higher body mass tend to have a higher maximal oxygen uptake. That looks pretty good to me. That's a good possibility. Let's keep reading. The strong positive linear relationship in the scatter plot, along with a p-value of less than 0.05, indicates an increase in body mass causes and increase in maximal uptake. These two are very, very close. All right, but this says cause. Was this an experiment? And the answer is no. It was an observational study, so we can't use the word cause. So D is incorrect. Be very careful that you notice whether or not we're dealing with an experiment or an observational study. And this says is likely due to chance. And no, it's not due to chance because it's a small p-value. If we had a p-value greater than 0.05, we might say it's due to chance. All right, so this is 27 is C, the best answer is C. Moving on to 28. An environmental group wanted to estimate the proportion of fresh produce sales identified as organic in a local grocery store. Construct a 95% Z interval, and they came up with this as their Z interval. All right, so here's our low, there's our high. And this is for winter. 6 months later in the summer, the group obtained a second random sample of sales from the store. The second random sample was the same size, that's important to note, as the first, and the proportion of sales identified what organic was 0.4. How does a 95% Z interval for proportion constructed from the summer compare with that of the winter? All right, the summer interval is wider and has a lower point estimate. Let's start off with the point estimates. Well, the point estimate for summer, the p hat for the summer is 0.4. Well, what was the p hat for the winter? Well, if I take, remember, my best estimate is always in the center of my interval. So 0.087 plus 0.133 and divide that by 2. And the p hat for my winter is 0.11. P hat W equals 0.11. Well, clearly the summer had a greater point estimate. All right. So the summer has a greater point estimate. So this is wrong. Lesser point estimate, greater, and greater. Okay, so we've gotten rid of a couple answers. We've gotten rid of C and we've gotten rid of A. Now the question is, are they the same width? So let's look at our formula. We have P hat plus or minus Z star, P hat, Q hat over N. Well, they've already told us, and so we're looking at our margin of error. They already told us we're working with 95%, so this is going to be 1.96 regardless. And this is going to be the same sample size. So we need to only worry about what's in the numerator. So let's do the winter one. The winter one, what's in the winter numerator? 0.11 times 0.89. And we're going to do the summer one in just a moment. Well, what's 0.11 times 0.89? 0.11 times 0.89. That's point. So our numerator is 0.0979 for winter. This is our winter numerator. What is going to be our summer numerator? Well, our summer numerator is going to be 0.4 times 0.6, which is 0.24. So our summer numerator is 0.24. So consequently, because our numerator is larger, with a larger numerator, we have a greater or a wider interval. So the summer interval is wider and has a greater point estimate. Now, here's the rule. All right, here's the rule. As P hat gets closer to 0.5, the interval gets wider. If you don't like that, you can say as P hat times Q hat gets closer to 0.25, the interval gets wider. All right. Both of those are they mean exactly the same way. It's just two different ways of thinking of it. So p hat gets closer to 0.5 as the interval. As p hat gets closer to 0.5, the interval gets wider. Or as p hat q hat, in other words, when we multiply them, gets closer to 0.25, the interval gets wider. So this one had a p hat q hat of 0.24. This one is only 0.09. So this one, the summer interval, will be wider. So the summer interval is wider and it has a greater point estimate. Number 29. In a standard golf tournament, golfers play 18 holes of golf on each of 4 consecutive days. For each hole, golfers keep track of the number of times they hit the ball before the ball goes into the cup. A golfer's score for the tournament is the total number of strokes needed to complete the tournament. The box plots below summarize the golfer's score who completed the tournament and golfer who competed in tournament 2. So we have tournament 1 scores, and we have tournament 2 scores. Based on the box plots, which of the following statements are true? More golfers played in tournament 1 than in tournament 2. No, the golfers' scores are more spread out. But we don't know how many are in tournament 1 or how many are tournament 2. There might be more in tournament 1. There might be more in tournament 2. It might be the same. We just don't know. All right. So the box plot with this information does not tell us how many played. In both tournaments, at least half, well, half is the median. So let's locate our median because that's half. At least half of the golfers completed the tournament with a score less than 288. And sure enough, the value is below 288. So our answer choice is B. We don't have to go any further. Number 30. Based on records kept at a gas station, the distribution of gallons of gas purchased by customers is skewed to the right. So we have a skewed to the right distribution with a mean of 10 gallons and a standard deviation of 4. A random sample of 64 customer receipts was selected and the sample mean, ooh, that's important. Not the sample, but the sample mean number of gallons was recorded. Suppose the process of selecting a random sample of 64 receipts and recording them, and here we have an N equal to 64. And the recording the sample mean number of gallons was repeated for a total of 100 samples. Which of the following best describes a dot plot created from the 100 sample means? First off, we don't care about the 100 samples, but we do care about this sample mean notation. First off, the mean will equal X bar because X bar is unbiased. And in this case, it's 10, but that doesn't help us out at all. But we have an N equal to 64, which is greater than 30. So that we know this is going to be normal by central limit theorem because we're talking about the distribution of the sample means. So normal by central limit theorem, that gets rid of A, B, and C. And what is our standard deviation of X bar? Equals the standard deviation divided by the square root of N. They told us our standard deviation was 4 divided by the square root of 64, which is 4 divided by 8, which is 0.5. So our answer to number 30 happens to be D. All right. Now, please be careful. They said the sample mean. So we know we're talking about the distribution of the sample means, and I also said it over here. Okay, the 100 gives us a vertical frequency. It has nothing to do with the actual distribution. So consequently, our distribution is a sample size 64, X bar equal to 10, normal by central limit theorem, and standard deviation is 0.5 because it's the population divided by the square root of N, or S divided by the square root of N, as the case may be. All right, thank you.